Welcome to my home. This is my air compressor.
This is a dual rocking piston compressor. It is used to compress air to two different pressures through the high and low pressure sides. The fluid enters through the intake valve and travels into the piston chamber. In the piston chamber, it is compressed and forced out through the exhaust valve at a higher pressure. The large piston creates the low pressure output and the small piston creates the high pressure output. Both pistons are connected to a shaft providing the same torque, and because the small piston has a larger crank pin offset, it creates a larger force. Since the small piston has a larger force and a smaller area than the other piston, it has the higher output pressure.
Let's talk about the assembly. The assembly is comprised of two separate pumps, each with its own piston and cylinder. The piston pumps the fluid into a system of valves and pipes which transport the compressed fluid to a container.
We want to calculate the characteristics of this pump, so we need to classify the motor. From looking at the coils, we can see that there are 4 distinct groups of coiled wires, so we know this is a 4-pole motor. We can calculate the speed of the motor using the number of poles, and calculate the torque created by the motor using its speed and given power. Using our measurements, we can estimate the output pressure of each side of the pump. Our calculated values are lower than the pressures given in the pump specs, but within the correct order of magnitude. Using our measurements of the small piston, we calculated the volume of fluid displaced in each stroke. Then, using the speed of the motor, we calculated the volumetric flow rate, and using the size of the output pipe, we calculated the fluid velocity. We completed these same calculations for the large piston. Now, we can characterize the system by finding the Reynolds number and pump-specific speed.
Combining the density and dynamic viscosity of air with our measurements for the pipe diameters and our calculations for the fluid's velocity, we found Reynolds numbers of around 7,000 and 17,000 for our small and large pistons, respectively. This means we have turbulent flow. Turbulent flow is hard to model because we use Reynolds averaging to add an extra term to the Navier-Stokes equation, which is Ft. Ft encompasses the effects due to fluctuations in the fluid, and we need analysis software in order to predict it. Reynolds averaging also assumes that our flow is stationary in order to decompose the velocity into its time average components, and for a piston air compressor with cyclic motion, assuming stationary flow won't fully capture the fluid's behavior. A higher flow rate with a lower pressure yields a Reynolds number that is higher and thus turbulent flow. Slower flow rate at a higher pressure means the velocity is lower and thus a smaller Reynolds number. Laminar flow, which is smoother, occurs at a Reynolds number lower than around 2,300 and can be modeled with the Navier-Stokes equation.
To further characterize the pump, we determine the specific speeds for each piston. To find the specific speeds, we used our calculated values for RPM and flow rate, as well as the pump's specified output pressure to calculate head. Given that the pistons function as positive displacement pumps, we determined that these specific speed values were on the low end of where a dynamic pump could work.
We've been covering the pump as we have received it. However, based on the pump specifications, you can connect the two sides of the pump in series for greater efficiency. By connecting two sides of the pump in series, you add the head of each cylinder together. This allows you to increase your overall head without changing the flow rate, overcoming larger head loss and resulting in a higher efficiency, which can be calculated using this equation. In order to connect pump in series, the pumps need to have the same flow rate, but our volumetric measurements of the cylinder have a different flow rate. Since the Mach number is low, the compressible flow model is used to model the system, but due to the high pressure, there may be compression in the air which we did not consider in our analysis. This would explain why the high pressure cylinder has a lower volumetric flow.
What if we were pumping honey instead of air? Integrating the Hagen-Poiseuille flow velocity distribution gives us an equation for the pressure differential across a pipe. We know that the force is pressure times area, so combining these equations, we get force required to push a fluid through the exhaust. This force is large, meaning that the pump could see mechanical failure if we tried to run it at the same RPM as for air. Because the flow of air through the port is turbulent, we can't calculate the exact force to push air through the exhaust port, but we can be confident that it will be lower than the force for honey. Running the pump with honey at the same RPM as for air would require more torque and power. To calculate this power, we first need to calculate the torque required to produce 314 pounds at the piston. We get a larger power than the motor is rated for, indicating we would need a more powerful motor to pump honey. Now I want to talk more about the models and assumptions we use to characterize the pump. One simplification we are making is describing the fluid as continuous, allowing us to use velocity, viscosity, pressure, and density. We are also using the Newtonian fluid model, meaning that the stress varies linearly with the rate of deformation. This works for air, but is not quite accurate for honey, since we are ignoring the effects of fluid velocity on viscosity. We also need to assume a no-slip condition to apply the viscosity-dependent relations to find force. Finally, we are assuming laminar flow for the honey since its Reynolds number is low.